Hello everyone, welcome to another lecture of fundamentals of ecology. In this module on populations, like population ecology, we often use a lot of mathematics, but this is fairly basic mathematics, and being familiar with some amount of mathematics is going to be extremely helpful in understanding ecological phenomena. In fact, it is often said that ecology is most quantitative of all of the biological sciences, and that is with a good reason. Ecology has a history of using mathematics for hundreds of years now. Okay, so now it is also true that in many colleges where students study ecology or more broadly biology, mathematics is very rarely taught. So therefore, many students might find it intimidating to look at equations, not because mathematics is hard per se in my opinion, it is because students have often lost touch. To remedy that, what I am going to do now is to have a lecture of about 30 to 45 minutes that sort of refreshes basic mathematics, and I would urge you to also go back and revise these simple mathematical tools using high school books. Usually the NCERT books from 10th to 12th is a good reference material for most of the things that I am going to cover. And when I am going to do this math refresher, I will ensure that I will also give as many ecological examples and contexts as possible, and these would be subsequently be very helpful. So let us start. Math refresher. For ecologists. Now to be clear, I am going to cover basic mathematics but not statistics. Okay. So let us start with the one of the simple things that you would have learnt at some stage, which is that of equation for a straight line. Okay. I am reasonably sure that most of you would remember an equation of this form: y is equal to mx plus c, where m stands for slope, c stands for y intercept, and when you draw a graph, okay, we draw x and y, mark the x and y axis, and then this is a sample straight line where this distance from the origin along the y axis is basically the y intercept, and how slant this is, is basically a measure of the slope. And in fact, if this our line makes an angle theta with the horizontal axis, then the slope would be given by tangent of theta. Okay. And the example that I have drawn here is that of positive slope. It is also possible that in many instances we have a negative slope, in which case the equation would look like this. So whereas this is an example of positive slope line, this would be an example of negative slope. Positive slope means that you are sort of like going up a mountain, climbing up a mountain, whereas a negative slope would mean you are climbing down a hill. Okay. So that is the sort of intuitive way to think about this. Now let us try to see this in the context of populations that we keep studying. Okay. Let us write down R as the per capita growth rate. and per capita growth rate basically means at the population level, if we normalize the growth rate per individual, what is that going to be, and this is basically the per capita birth rate minus the per capita death rate, where B again is basically the number of offspring per unit time, and D is basically a measure of death per unit time, okay. And all these entities are measured per individuals. Now in ecology we often study the concept of density dependence and density independent populations, right. Now when we say density independent population growth, what we basically mean is that this per capita growth rate R, if I plot that on the y axis, that does not depend on the population density x. If x is the population density, and R is the per capita growth rate, if this is a constant and if it does not change with the population density, we call this density independent population growth, right. So now this is an example of a straight line where, okay, let us say this is R0, R0 is the value of the constant that does not change at all with the population density, therefore, and in fact the slope of this line that I have drawn is basically 0, slope that is equal to m is basically equal to 0, right. So therefore the equation for density independent growth rate would be that R of x does not depend on x, it is just merely R0, okay. And of course ecologically speaking, such a scenario arises when there are abundant resources, so that the number of births per individual and the number of deaths, the probability of death per unit time, they both do not change with the densities, okay. So this is the simplest example of a usage of straight line in ecological context. Now let me show one more example, which is naturally density dependent. So this captures, in when we think of density dependent population growth, we often try to capture the fact that the amount of resources are limited, therefore the per capita growth rate cannot stay constant with population density. Instead it starts with some high value, let us call that R0, that would, when there are basically when the population density is very low, everybody has abundant resources, so they are at the maximum possible per capita growth rate, but this declines with the population size or the population density. Let us say that at a value of k, when the density reaches a value of k, the per capita growth rate has become 0, and for any values beyond k, any densities beyond k, we have a negative per capita growth rate, and k is basically a measure of carrying capacity of the system. Now how do we write an equation for this? Okay. So we want to know how does the per capita growth rate now depends on the population density. Now we have two information from this graph, right. When x is 0, when the density is 0, the value of the per capita growth rate is R0, like this one which is sort of already telling you that the y intercept of the straight line equation is actually is R0. Remember that this was the y intercept and this is basically R0, right. Now we have one more information, which is that when x equal to k, the per capita growth rate is 0. To determine an equation for a straight line, we only need to know 2 points, and then we can determine the equation for a straight line uniquely. Okay. So, now let us do that. So, let us now use the formula y is equal to mx plus c, and remember that y in our case is r of x. So, therefore, r is equal to, we do not know the slope m, we need to determine this, x is population density and c. Now, just recollect that the first information here gives you that the value of c is basically r 0. So, basically if I set x equals 0, we know that r is equal to r 0, the first term will be 0, second term will be c, this means that c is r 0. Basically whatever I just argued by looking at the graph can also be done algebraically here. So, of the 2 parameters in the straight line equation, we have now found one, which is c. Now, what is the value of slope? Okay, so, to do that, let us now use the second information, which is that the at population density k, we know that per capita growth rate is 0. So, left hand side becomes 0 in the r is equal to mx plus c equation. We need to find the value of m, and the value of x is k, and this is r 0. Okay. Now, this now tells me what is the value of m by moving terms on different sides. So, basically if I bring r 0 to the left side, or rather I could bring the equation mk to the left side and change the signs, and we will find that the slope is nothing but r 0 divided by k. We have basically now found both the constants in the equation for a straight line, therefore, we can now write the equation for straight line. So, r is equal to mx plus c, m is minus r 0 by k times x, and c is this, and further I can simplify this by taking r 0 as a constant and writing the positive term first, which is the second term here, and then rearranging the terms, we get this equation. So, this basically is an equation that captures the graph I showed you. Okay. So, if I were to go back and write the equation now, r of x would be r 0 times 1 minus x by k. Once you have found the equation, it is always important to plug in the numbers, specific values, and make sure they make sense. For example, if when x equal to 0, the second term goes off, I am left with r is equal to r 0, which makes sense, and when x equal to k, the second term basically is 1, and 1 minus 1 is 0, therefore, r is 0, which again makes sense. Excellent. So, this is thinking about per capita growth rates and simple straight line equations. Now, let us now move on from straight line equations to quadratic equations. So, quadratic equations are generally of this form: ax square plus b. So, y basically now depends y basically now depends as a quadratic function of x square with some coefficient a and with some constant b. Okay. Again, it is useful to be able to plot some of the basic curves. Let us consider a is equal to 1 and b is equal to 0. In this case, basically we have y is equal to x square. Let us now try to plot this simple curve. So, we mark the x and y axis. Okay. Let us now try to plot this. When I ask students who have not done math for a long time, what they do is the right thing, which is tabulate for various values of x what is the value of y. So, if x is 1, y is 1, if x is 2, y is 4. So, mark this, and if x is 3, it is 9, which is way above there. Now, as you see, it gets really hard to plot on a simple graph like this unless you have you do it very carefully, and then you try to connect these, and of course, when x equal to 0 you have 0. And another important thing to note is that if x is replaced by minus x, the function does not change. So, basically if I think of any negative value, because the square of a negative is positive, it does not change. Therefore, this function is symmetric around the the y axis. So, the same values will be there even if you look at the left hand side, the minus negative axis. But here is the thing, important thing, people often do not worry what happens between 0 and, is it a straight line here? That is not right, this is wrong. Okay. So, this function actually has an interesting behavior that between 0 and 1, although it is increasing rapidly after 1, okay, between 0 and 1 actually it is a value smaller than y is equal to x. So, in fact, take for example x equal to 0.1, y then becomes 0.1 square, which is 0.01, right, which is actually smaller than what you started off with. So, in fact, in the window between 0 and 1 it actually has a shape like this. The shape remains same, but the values between 0 and 1 are actually smaller compared to a straight line with y is equal to x. Okay. So, the drawing quality is not great here, but you should practice this using your own hand as well as using various plotting tools. Now let us now think of an ecological context where an equation for a quadratic equation makes sense, is useful. Again, let us go back to the example of density dependent and density independent populations. In fact, I would take the example of density dependent population. The specific example being it is a linear negative density dependence. Negative density dependence, you remember we had this, right. Now, this is per capita growth rate, right, this is per capita growth rate. If I now ask what is the population growth rate, okay, let us denote the population growth rate by f of x. So, remember that per capita is for an is basically per individual. The population growth rate would be basically per capita growth rate times the density. So, we need to multiply density with the per capita growth rate, then we get the entire population growth rate. So, which basically means f of x is r of x times x. Now, if I now substitute r of x is equal to this equation and then rearrange some terms, I will get this. So, the population growth rate for the simple density negative density dependent equation we considered actually is now f of x is equal to r 0 times x times 1 minus x over k. Okay. Now, if I expand this, the first term will be r 0 times x and the second term will be r 0 x square divided by k. So, here you see that we have a quadratic term in the equation for the population growth rate. If I were to compare this with the general form here, this is same as saying that I have a positive constant, but a negative coefficient for the x square. Okay. Now, let us now try to plot this equation. So, we will mark x axis and the y axis will be now the function f of x, which is the population growth rate. Now, let us think about this function. Now, the first thing to note is that since we are interested in biological populations, so the negative values of x means negative population density. So, it is not particularly relevant for an ecological context. So, by and large we can ignore what happens on the negative side of this, this part we can sort of ignore what is happening there. Okay. So, we only focus on the positive side. Again, now positive side, how much should I focus on, and if I look at the equation, it actually gives you some hints. Okay. And we know that K is the carrying capacity, and biologically and ecologically we have an understanding that population cannot be terribly larger than carrying capacity. So, what happens up to carrying capacity is an important thing. So, that is therefore let us mark the carrying capacity K there, and then let us now look at what happens for small population sizes, large population sizes, and so on. Okay. Let us look at the smallest population size, which is basically no populations, x equal to 0. So, when x equal to 0, f of x is basically 0 times something, and therefore it is 0. So, because of this r0 times x term, the entire population growth rate is 0 when there is no individual at all. Okay. That makes sense. And what happens when x equal to k? Again, the second term now becomes 0. When x equal to k, x by k is 1, k by k is 1, and 1 minus 1 is 0. So, therefore, f of x again becomes 0. So, we have identified two locations, two values of population density where the growth rate is 0. Now, let us look at what happens in between. Is it a positive number? Is it a negative number? Let us say look at some arbitrary value of x. So, this number is positive in that window, and this number when x is less than k, x by k is less than 1. Therefore, 1 minus of something less than 1 is positive, right. So, therefore, this is positive, this is both the terms are positive in this window, and therefore, the entire function is positive in between. So, we see that in the intermediate window the f of x is positive, and it always remains positive in between, and if you make careful attention, you will find it is basically a inverted quadratic function between 0 and k, and then it would the population growth rate then becomes negative once the population crosses x equal to k. Okay. So, this is how this function looks like, how the population growth changes with population density when the per capita growth rate is actually a linear function. Okay. So, now having learnt straight line, quadratic equation, let us now move on to another function that often we use, which is a power function, a general power function, okay, where f of x is some constant times x power a. So, we call c is a constant, a is an exponent of the power function. Okay. Of course, when a is equal to 1 we have a simple linear equation, when a is equal to 2 we have a quadratic equation, but we can also have non-integer values of a, right. For example, if consider the context of species area curve. So, species area curves are an important relationship that we study in ecology. It basically sort of tries to capture how the number of species, okay, change with the area. Okay. So, it often follows this sort of a form, which is as you increase more area, the number of species do not increase proportionately, because the number of new species keeps on reducing with the number of new area with the new areas you are adding, right. Okay. So, it has this sort of a form, and in fact empirical fitting of this of these data to shows that if we denote the number of species by S and area by A, S follows a power function of this form, and where typically Z is of the order of 0.1 to 2. Okay. So, this is actually not an integer value. The important point to note here is that the Z is not an integer value, it is also less than 1, it is also a value less than 1. Okay. And typically these are they do not saturate, but they keep on increasing forever, but they do not increase at a faster rate, the rate of increase is small. Okay. Now, let us look at another curve that comes up very frequently in ecology, is that of exponential function, right. So, we often study population size, let us denote that by n of t. We can also denote x of t as a density, and that often increases exponentially with time, and we know we write that in this form n of, so where n0 is the initial population, right, and this is the population of after time t, and r basically is the per capita growth rate. Okay. So, and this happens in the context of density independent populations, and the graph of how population changes with time would look like this, sort of rapidly increases. Okay. Now, so let us now look at couple of more functions before we move on to a very important concept. So, one other function I would like to cover is logarithmic functions, which we denote as y is equal to ln of x, where ln is basically logarithm with respect to base e. So, base e is the what is most frequently used, sometimes people may use base 10 as well, but base e is what is most importantly used. And if we were to again plot y as a function of x, it is a increasing function. It can take negative values when x is less than 1, okay. It takes negative values when x is less than 1, and it takes positive values for x greater than 1, and it increases at a relatively slow rate. Okay. Now, it is used, before I go forward, I have been using this word rate, so I will get back to this very soon because it is really important and very useful as well. But before I do that, let us look at couple of useful and interesting properties of logarithmic functions. Okay. So, let us say I have a function y, which in turn is a product of two variables x and z. If I take a logarithm of y, it turns out that logarithm of product of two things is basically a summation of the logarithms. So, logarithm is an useful function because instead of, let us say, for whatever reasons, let us say if I do not want to deal with variables x and y directly, and if I do not like the products, I can convert them to an additive process by taking logarithm on the both sides. Okay. So, this is one useful property of logarithms. Now, consider y is equal to e power x. Okay. Okay. Now, what happens is if you now take the logarithm, the exponent becomes a coefficient, and the the logarithm, the e now is basically in the logarithmic function, but logarithm of e with respect to base e is nothing but 1. So, you basically have logarithm of y is equal to x. So, you can consider more slightly more complex functions such as 2 power x, then we will have x of log 2, okay. And imagine if y was e power r x, in such a case if I take the logarithm, r x comes out on the comes as a coefficient, and of course logarithm of e is 1, this basically becomes r of x, okay. So, logarithm has a useful property that it converts sort of multiplication to addition, and it basically reduces the sort of magnitude of number. Logarithm of a number is a much smaller number than the original number, and that sort of is captured in this curve, that it is actually a decelerating function, okay. Now, we have now sort of learnt various functions. These are all often very useful, and I have also given some examples, right, of how these functions are relevant in the ecological contexts, okay. Let us now discuss how rates and calculus are related. So, I kept on using the word rate, the rate of increase of a function. This function is decelerating, this function is increasing. So, what do I really mean by that? So, how do we go about thinking about the rates, and this basically is the idea of calculus. Idea of calculus is to measure the rate of change, okay. So, now to illustrate that, let us consider two functions which we have learnt now. One is y is equal to x square, okay. We could consider y is equal to, actually we could consider a quadratic function, a linear function, and also y is equal to e power x. So, we know that all of them are increasing functions. Let us draw each of these functions, x here, y there. Let me first draw y is equal to x, that would go through origin, has a slope 1, it has a constant slope, it has a constant, the slope basically is the rate of change, right, because a steeper line means more slope, and the characteristic of a straight line is that its slope is constant as a function of x, and the slope is really nothing but the rate of change. That means the rate of change of the function y is equal to x is constant and does not depend on x. On the other hand, if you think of y is equal to x square, it would look like this, right. This function clearly visibly is more rapidly increasing than y is equal to x, okay. On the other hand, if we think of, and that is fairly easy to see, however, think of y is equal to e power x, okay. E power x starts somewhere here, and then I am not drawing this to perfect scale, but only to illustrate the point that e power x would look something like this. Just to be, again, I want to caution you that I have not drawn all the points of intersections accurately here, but only focus on the shape of the equations. It is easy to see that both y is equal to x square and y is equal to e power x are more rapidly increasing than y is equal to x. That is very evident from the graphs themselves. But between the two, y is equal to x square and y is equal to e power x, which of them is more rapidly increasing, okay. Now, this is where the formal tools of calculus becomes really handy. So, basically calculus helps us know for every point along the x axis what is the slope of the function. For a straight line it was really easy because the slope was a constant, but that is not true for any general function. Basically, if we have a function that depends on x, the derivative of the function which we write as df by dx. Okay. This basically is nothing but slope of the function. And remember that this derivative itself could change with x. Okay. But the key idea to remember is derivative basically is the slope of the function, or the rate, it captures the rate of change of the function. Okay. So, now I am not going to go into much more details of calculus, okay, and then providing you with a table of the functions that we all discussed today and what are their derivatives. Okay. So, let me write the function here and let me write the derivative. So, let me start with y is equal to mx plus c. If f of x is mx plus c, then the slope of this is a straight line, it has a slope of m, and derivative is nothing but slope, its derivative is basically therefore nothing but m. If we have a function ax square plus b, which is a quadratic function, okay, then we only need to take the derivative of the x square term, because constant actually does not influence the slope, and the slope for this will be 2ax. And what is important and interesting to note here is that the slope depends on the x itself. As you increase x, the slope is actually increasing, and that is sort of precisely what you are seeing here in the blue curve as well as in the red curve. As you increase x, the function is increasing more and more rapidly. Basically between 4 and 5 it increases rapidly, but between 9 and 10 it increases even more rapidly, that is the idea. And if we can think of more generally x power n, then the derivative of that would be n x power n minus 1. Okay. On the other hand, if we think of logarithm of x, the derivative of this function is 1 over x. So, here is an important contrast you must note. Both the quadratic function, the linear function, and the logarithmic function, they were all increasing, right. The key thing is the logarithmic function is increasing, but the slope is actually reducing. On the other hand, the slope was a constant for a straight line, slope itself is increasing with x, but here the slope is decreasing. For the power function, it really depends on the value of n. Okay. And let us look at another important function, which is an exponential function. The slope of the exponential function is actually itself. Okay. So, it is very interesting in the sense that if you take the derivative, you get back the same function. That means at every point it is as rapidly increasing as the original function, whereas logarithm, okay, the slope is 1 over x, which actually is reducing with x, and therefore it is a fundamentally a different function. Okay. So, I encourage all the students who have not done mathematics for some time to revise plotting functions, as well as the derivatives, get some familiarity with writing equations, plotting functions, and it would really help you a lot in being able to make sense of ecological patterns in a much more rigorous way. So, thank you very much. So, I will end my this lecture for now, and these tools that we have learned will be used, and I will reiterate some of the points as and when necessary. Thank you very much.